Experiment 8. As is now the pattern, the experiment will all be on Canvas. So that means turn everything in, pre-lab data, post-lab, all as one PDF file for your due date, whether that's Tuesday or if you're the Thursday class, April 28th or April 30th. And remember, all these times are at the end of the day. Exam 1 in practical, I'm still grading that, so I plan to get that back to you as soon as I finish it. Please see me during office hours if you'd like to go over any of these experiments. Other places you can get assistance, that would be discussions with Jamie or Kara, your lab assistants, on Tuesday or Thursday. Go to Canvas and they're there ready to ask and answer questions. There's quiz 4 on Canvas for this experiment, so I encourage you to look at that. We will have a brief discussion over what's happening in experiment 8. And please note, experiment 9, we're on this pattern. We did 6 experiments, exam, you got 6 more experiments, and an exam. So that's what's ahead. So you might start with, well, why would we synthesize new compounds? And I have to admit, this is one of the favorites of CHEM152L students in the past, because you're making something. And in this case, you're making something of practical value, of something that's probably impacted all of us, whether that's aspirin or some pharmaceutical. Maybe you've taken some pharmaceutical in life and it's helped you, okay? So that's a primary reason right there. So what you're gonna do is watch the videos and make observations how you can synthesize aspirin. The videos are pretty reflective of what we would do in lab. There's a couple of differences. Then you also have videos of purity tests. As you can imagine, you just don't make something and like look at it and say, oh, that's white powder. Okay, here, why don't you take it now and see if it helps you feel better? You can't do that. You have to have purity test to determine, did I make what I said I was gonna make, and how pure is it? And how pure does it need to be? So it depends on the area you're in, but you could synthesize new compounds for a variety of reasons. Most of my graduate work was synthesizing new compounds and is for environmental reasons, removing lead, toxic lead from water. You could synthesize new compounds to make reactions go faster. You could synthesize new things that have never been made before. So there's a variety of reasons. We're looking at one. We're looking at aspirin. And salicylic acid was known to relieve pain. Great, that's fantastic, pain reliever. Well, as you've probably seen pharmaceutical commercials, then there's the list of side effects. So salicylic acid also caused stomach pain, okay, stomach indigestion. So aspirin was synthesized to keep the pain relief, but then to minimize the effects on the stomach. Okay, so here we're synthesizing something to modify side effects, but then to keep how it can assist our bodies. So you'll watch and you'll see adding reactants together, you'll see filtration. There's a lot of good techniques in here, introduction to synthesis. They do heat their reaction. In the video, we don't heat our reaction when we do this at Miramar. Reaction still works the same. So it's very similar, but there are some slight differences. And maybe you've heard this term before, but a catalyst is used to speed up a reaction. Okay, so sometimes reactions will not work without a catalyst, or they'll be very, very slow. So this lab usually takes an hour and a half, maybe 2 hours at most, because it's a very fast reaction. You can recover your product, test for purity, and be done very quickly. So the catalyst helps in that. Test for purity, what you're going to watch is reaction with iron 3 chloride, and that's in your lab packet, so you can write down your observations. What you're trying to see is how does the starting material react with iron 3 chloride, and how does my final product react with iron 3 chloride? They should be different. Okay, if you have, if you'll see the starting material is white, the final product's white. Well, so you have to go deeper than just saying, well, it's a white powder. You have to test the reaction. If they're 2 white powders and they react the same, then they might be the same. Well, what we're looking for is they should have different reactions. Another test for purity is melting point. And this is a really common technique used in organic chemistry. So if you plan to take organic chemistry, you'll definitely do this more. And what you're going to see is that in the video it talks about aspirin having a melting point of 135 degrees. Well, salicylic acid, what you started with, again, white powder, 159 degrees. So definitely different. So if your final product melts around here, you're good to go. If your product melts around here, there was no reaction. So that's how we use these purity tests. So I want to point out a couple of things. These are really complicated molecules. Like I said, this is organic chemistry, so organic molecules. But this is what you've been doing. Molecular formulas. Okay, it's made up of carbon, hydrogen, oxygen. You've done names. These are just common names for this. Some of these are systematic with, this is an anhydride. These are acids. But what I want to point out is this is the compound that relieves pain, but this is going to be modified. Okay, remember that side effect, don't want that side effect anymore, and it's like Lego pieces. You see how we're taking this piece from this molecule, and I'm going to remove that H and put the Lego piece on there. So now, if you take a look, the new molecule, acetyl salicylic acid, or aspirin, that's our aspirin that we take, this is all the same. Okay, we just add this piece right here onto the already existing oxygen. So that's synthesis. It could be as little as that. In this case, remember, this takes a catalyst to speed it up. So sulfuric acid is used here as the catalyst to speed this up. So this is the reaction for the synthesis of aspirin. What you're going to also working on in this lab is a limiting reactant problem and how to calculate percent yield. This is a really important topic when you're doing synthesis. As I mentioned in graduate school, the synthesis that I did, I would have to purify the compounds, and then I'd have to report, did I have a 90% yield? Did I have a 20% yield? And then when you publish in journals, people look at it and say, oh, look at the yield on that reaction. I want to redo that reaction just like they did it, or I want to change some things so to improve the yield. So to do these kind of problems, I've got one listed here for you. Magnesium reacts with oxygen. So here's the balanced chemical reaction. I encourage you to pause the video and do the calculation if you're familiar with calculating limiting reactant problems. So what you should have done in this problem is been looking for the theoretical yield. Okay, we want to figure out how much is it possible that we could have made. So to do this, you need to do two calculations, one with magnesium and one with oxygen, and it's stoichiometry. You need to convert the oxygen to magnesium oxide, convert magnesium to magnesium oxide. So this was a reaction that was previously in this CHEM152L. And then to get percent yield, we need to factor in how much we actually got. Okay, so this terminology is really key here. I want to briefly go over. First, the two stoichiometry problems. Okay, grams of magnesium converts to moles of magnesium. The mole ratio, which comes from the chemical reaction here, 2 to 2, gets you to moles of magnesium oxide. So that's one stoichiometry problem. The second one is our grams of oxygen. Remember, molar mass goes to moles of oxygen. This mole ratio, different substance, that's a 1 in front of there. So that converts it to now 2 to 1 ratio. So that's your moles of magnesium oxide. So then we look and compare these numbers. 1.75, 2.11. So the least amount of product is what actually can be made. This is the examples usually given in the books are like if you're baking and you have enough eggs to make 12 cookies, but you have enough sugar to make 24 cookies. Well, you can't say, I'll just use my sugar and make all 24 cookies. You don't have enough eggs. So you can only do the least amount of product. That's the same concept here. So you take a look, say, well, this is the least amount of product. that means that the magnesium is the limiting reactant. That's like the eggs, it runs out first. The magnesium runs out first, gets you to the moles of magnesium oxide, and then if you convert to grams of magnesium oxide, this is your theoretical yield. Okay, so if you've got theoretical yield, and we were given actual yield, then we can get percent yield. How did it go? 79%. That's pretty good for synthesis reactions. Some of the reactions I would do would be 80, 90% yield, fantastic. Some would be like 20%. So this is the synthesis, what you'll be doing, and then these are the calculations that you'll be doing for this experiment.